Welcome to The Gig. I'm Johnny O, and today I want to talk about predictions in computing. Not only computing, I'm going to divide it into two sections. We're going to talk systems, predictions in futuristic systems, and futuristic networks. So, right now, what we're seeing is SSDs getting really, really good. SSDs essentially run like RAM. I've explained this in previous videos. They run like system RAM, and no data is going to run faster on your computer as it does when it's in upper memory. That's the memory that Windows uses. So when you boot your computer, it basically is taking the operating system off the hard drives and loading them into upper RAM. Your programs, as you use them and they load into upper RAM. That's what they mean when they say launch the program. They're taking it off the hard drive, putting it into RAM. Because in RAM, it runs really, really fast. So SSDs are becoming like RAM. In fact, they work like RAM now. They're not spinning disks anymore. They're solid-state drives. And the manufacturers of your RAM chips are also the manufacturers of your SSD drives. They take those RAM chips, and they're slightly different in design, but they take the RAM chips and they put them in configurations like hard drives, and they run on hard drive buses, and that's why they're so fast. They're like 10, 20, 30 times faster than a traditional spinning hard drive. For example, I think on a SCSI RAID with 2 spinners, to give you an example of how fast these things really are, is on a server you would have a bus called SCSI, and it was really fast. And you would be capable of something like less than 10 seconds, probably 7 millisecond response from your spinning hard drives in RAID, okay? In RAID 0, like a RAID for performance. And you'd be capable of maybe, I'd have to check it, but I'm just guessing, okay? Maybe 50 IOPS. Maybe. Depends on the hard drive and how big the cache was on the hard drive. An IOP is an input-output request. That's what they call them, IOPS. That's how many times an application or the operating system is requesting data from a hard drive on your system. It's called an IOP. Now, these SSDs not only are, let's say 7 millisecond response time from the hard drive. SSDs are phenomenally faster than that for response time. Phenomenally faster. I mean, I'm not even going to go through the numbers. That's how much faster they are. Let's say 10 times, 100 times quicker, easily. And the IOPS they're capable of are in the thousands. Thousands of IOPS per second. That's what they call it. Input, output per second, IOP. They could do thousands of these a second. And when you RAID them, the servers are capable of millions per second. I've heard over 7 million IOPS per second some of these SSD RAIDs on servers are capable of. Insanity. Insanity. I can't believe they're even making spinners anymore. So with that in mind, the hard drives are designed much like your RAM. And your CPUs actually have RAM burned into them, right? Right into the chip. It's called your L1, L2. I think some of the Intel chips even have L3 and L4. Okay, that's level 1, level 2, level 3 cache. They call them L1 cache, L2 cache, L3 cache, L4 cache. That's level 4, level 5, level 3, level 1 cache. It's just cache. It's a certain amount of memory that they burn right into the CPU. And anything in that L1 will run at full clock. So parts of your app are coming out of RAM and they're being pushed into your L1 cache where the CPU processes them. And the bigger your L1 cache, basically the better your benchmarks on your CPU are because it will process faster. Things going into the L1 are processed at full clock. So what they've done, and the reason the Intel chips do benchmark better than the AMD Ryzen chips is because of their L1 cache. It's not for any other reason. So I mentioned on a previous video, the Ryzen chips have more than one CPU burned into them when they're made. Instead of using that space for more CPUs, Intel used that space for more cache. And these benchmarking programs actually measure the cache and give the CPU a score based on that cache. And in real world, they have real world tests where they don't score it like that, where they test this exact process or set of processes on this CPU and this another set or the same set of processes on another CPU. And that's called a real world test. It could be a render from Adobe or something like that. And then they get the actual real world benchmark from the CPU. And what they're finding is the Ryzen chips, the better the application is ported to run multiple threads, the better the Ryzen chips do. And any application across the board, Intel usually wins. It's inching out the Ryzen chips slightly because they have those big caches. And what they mean by caches is they're burning RAM right into the chips to make them faster. That's what it means. And so what's happened is we've seen hard drives basically turn into RAM. We're seeing these CPU companies put more RAM into their CPUs. So in the future, what we're going to see is when you buy a CPU, the RAM is going to be burned right into it. That's my prediction. That's how you're going to buy a CPU. You're going to buy a CPU, and it's going to be a certain clock cycle or whatever, a certain core count. Maybe you're going to get a CPU with 128 core count and 56 gigs of RAM, and it will be a chip. So if they're burning the CPUs into the same silicon as they're burning RAM, and you can see how the trend is going where hard drives are becoming like RAM and CPUs are getting more and more RAM burned into them, you're going to be buying a chip with your computer that will have the RAM burned into the CPU. It'll be right there. It'll be part of the same socket. Your CPU might be this, like a rectangle like this with a bunch of RAM on it, or it might be a big square with a bunch of RAM on it, and you put it into your motherboard. That's how it's going to work. Now that you have that idea in your head, think about this. So if they're burning RAM and all kinds of logic into the CPUs, why not burn the CPU chipset, the motherboard chipset into the CPU? So the CPU chipset's burned into the CPU. They're going to be doing that too. It wasn't that long ago that the Northbridge RAM controller on the motherboard was on the motherboard. Now it's burned into every CPU, AMD and Intel. So they've taken that core logic and they've burned it into the CPU to speed up the system. AMD was the first one to do this in 2003, I believe. Intel copied them by 2007. They copied them with the I series and Core 2 Dual. That was Intel copying AMD. I did a separate show on that. So they're taking, think about it, they're taking the core logic that is built into the motherboards. They're burning that into the CPUs as well. They're taking RAM and they're burning that into the CPUs as well. So what you're really going to see in the future is you're basically going to buy a piece of glass and a piece of silicon, a big piece of silicon that you plug into, a power supply. Gives you your RAM, it gives you your storage, it gives you all the core logic that's on your motherboards. Your motherboards are going to be pieces of glass. The RAM and everything's already built into them. Now, way in the future, and I don't know how close they are, I haven't looked at it in about a year, but this is all based on electronics. What we're going to see is photonics. Okay, so fiber optic is photonic. Okay, what we haven't seen, but 3 or 4 years ago, the Australian university, or was it a company? I can't remember if it was a company or a university. They demonstrated a basic photonic CPU. And that means instead of the CPU running on electricity, it runs on photons, it runs on light. There's not only a speed advantage to that, there's a power consumption advantage to photonics. But the manufacturing process is really tough, because they don't have storage mediums for photons. They have storage mediums for electrons because they behave differently. So we're going to see that in the future. I think the the motherboard that you buy will have everything on it. It'll have the CPU burned in. It's going to be burned into a single piece of silicon. Your RAM, your storage, all the motherboard functionality, all the logic chipsets that you see on your motherboards, they're going to be burned into the silicon directly. Even your storage and your RAM. That's what's going to happen. And way in the future, we're going to see that it's not running electronically. It's going to be running photonically. Now, with that in mind, if you picture a system as a piece of glass inside of a power case to power it and cool it, oh, with photonics, you won't need cooling. You won't need cooling. It uses hardly zero electricity. Lasers don't use very much electricity at all. And they don't produce heat, like none at all. So the heat is out the window. The huge power consumption is out the window. We're not using that. So that's where we're going. We're going to photonics. I believe that will be the next big step. I mean, the next real thing we're going to see in computing is photonics. Now, with photonics in mind, I want to talk about networking. I want to talk more specifically about cluster grid networking. Right now, most networks' backbones are already photonic. They're already fiber. But what we have is we have a middleman that we really don't need. The only reason they use the middleman is to meter our bandwidth, and that's the ISP. And as you know, ISPs don't do much. They don't do much of anything. They set up the infrastructure. Once it's set up, essentially what they do is they just make sure bandwidth is being provided to their customers. But once it's in place, and they'll make mega bucks off of it. And that's really great. It's mostly monopolized. I believe in Canada, it's like 3 major ISPs. In the States, it's 3 or 4 ISPs. There might be some more localized ISPs, but they have to run over the backbone of the monopoly players in those countries or in those areas. There's always monopoly players, and we don't really need them. Cluster grid networking is a concept that I read in a book called, I can't remember the name of it. It was really good. Oh, yeah, that's it. There was 2 books written. The author wrote a book called Microcosm in the 1980s. And I read that in the 90s, right? And his prediction was there's going to be microchips in everything. And his prediction was correct. By the 90s, it was correct. Even your food products, they can take a very simple chip and they can put it inside the food product if they want. I believe they use it only for, and then when you take your cart, little tiny chip inside the box of, you know, cereal or meat or something, you just take your cart out, boom, it deducts your account immediately. Or you tap your card, or you won't even have to do that, right? So he predicted this in the 1980s, that everything's going to have microchips in it. And he was correct. Everything has microchips in it. Your camera, your phones, your TVs, everything. He also wrote another book in the early millennium called Photocosm. And he predicted a new network grid called cluster grid network. And what happens in a cluster grid network is everyone is connected to everybody else beside them, right? So your neighbor and you have a fiber connection between you. In fact, the whole neighborhood is set up in this grid. And what happens with DNS, Domain Name Service, this is the central registry that tells you the IP of the URL that you're going to. Yeah? So if you go to Microsoft.com, it's very easy for us to remember Microsoft.com. It's a word. We can remember words very, very clearly. We don't memorize numbers as well. So what the DNS server does is it takes that name and it resolves it to an IP, because Microsoft.com is just an IP that Microsoft has chosen to publish their website on. It's just an IP on a server somewhere. So all the servers just understand IPs. That's all they understand. They just understand numbers. To make it easier for us to interact with all these computers is they give them names. Microsoft.com, eBay.com, Amazon.com, you know? And these are just IPs. As far as computers are concerned, they're just IPs. But there's a service, a middleman, that helps them out. And it takes the IPs and it resolves them to names. Amazon.com is just an IP somewhere, and vice versa. And it gets quite complicated where Amazon.com and then Amazon.ca, then Amazon.uk, and they will use several mirror sites within that country or region to replicate their site, to make their site faster in that region. So these sites are replicated all over the planet through DNS. Yeah? Now the ISP provides the user with access to basically backbones with DNS service. That's all they do. They don't do much. They don't really need to do much once they come to your house and the line is going into your house and you have the access point for their network, whether it's DSL or cable. They don't actually have to do much. You're just going to go online. Okay? They're going to provide DNS service. But then there's public DNS service. It's actually called public DNS service. Or you could use the Google DNS service. Okay? In your network settings, you just tell it, don't go to my ISP for DNS, go to Google for DNS, which is 88888 or 8844. Okay? And then there's public DNS that do this. Because if everybody in a city, if a large portion of that city, the market for internet access within that city, using the same ISP, the ISP is going to basically give them the same DNS. These ISP DNS servers get very congested. They're not as fast as public DNS services. And so a lot of people like me, I use public DNS or outside DNS, and I'll use Google as a backup. I don't use the ISP DNS. It's a lot faster not to use the ISP DNS. So we don't really need the ISP for DNS. We don't. We did 10 years ago. I mean, there was no public DNS. We did 10 years. We don't anymore. What we do need them for is circuit access. We have to access that data circuit, whether it's over cable or if it's over DSL. But with cluster grid networking, you don't need that. You just need any fiber connection coming to your house. And as long as it goes to another house or another couple of houses or to the neighborhood, that's all you need. Then each neighborhood is connected to each other neighborhood, and any business in that neighborhood is also connected to the same grid, And each computer, actually, you don't even need DNS. Well, there might be some central DNS service needed, but you don't really need it because the network cards should have a DNS cache in them. They should have it now. They don't, but they should. And so the DNS is all cached locally on every node, and every node is connected to every other node next to it. This is cluster grid, and this is how it will work. And you don't really need to meter it. The reason they haven't implemented it is it's hard to meter. If everyone else gets all the service and circuit access just from being connected to any fiber line going into their house, you don't need an ISP for that. The technology is getting there to do this very efficiently as well. I think ISPs will be a thing of the past in the future. Just like you don't really notice who your power company is. Everyone you talk to will know who their ISP is. I got Comcast, or I got this service or that service, or I got Bell DSL or something like this. But they have a power company, a local power company that's a utility. And so they don't, I mean, the utilities do farm it out to smaller companies. You won't know who they are. It'll be the same with ISPs. There'll be a utility. And simply, you just have to be connected to the grid. And you get all your DNS data and your circuit access. That's it. That's all you really need. If there's any network problems, it's probably at your computer, right? Or line has been severed somewhere. And then that's a utility problem, right? Then the utility company comes and fixes that line. For ISPs, I think they're a thing of the past. I'm sorry. I mean, they're going the way of the dodo, right? Same with antivirus companies. They're going the way of the dodo. Anything that an antivirus company does is built into Windows already. Anything an ISP does is rudimentary. We don't really need DNS from them. And we just need circuit access. Well, it's just like your power company. You just need circuit access to your power, and then they meter it. I don't think they'll be able to meter bandwidth. There'll just be too much pushback. I mean, it won't be metered the way, power is metered. I'm sure that's their hoop dream, to be able to do that. It just won't happen. That's my prediction for the future. So what you're going to have is you're going to have a silicon network, okay, a glass network, a cluster grid running all on fiber with these local caches and everything like that, as I explained. And then your computer is also just going to be a big piece of silicon, okay? And it's going to have everything built right into it, burned into it. And that's why it's going to be so fast. It's going to be really fast. Your computer will be really fast. Your network will be really fast. And hooking up another computer to another network on the cluster grid will be pretty easy. And if you want to know more about that, the book is called Photocosm. I can't remember the author's name. You could look it up, Photocosm. And he was the guy who predicted in his book Microcosm that microchips will be in everything. He's also predicting, and his prediction is coming pretty good, is Photocosm, fiber connections to everything. So another thing I wanted to mention before I go and end this segment is Moore's Law. Moore's Law is still valid. What Moore's Law is when Intel and these companies, I think one of the founders of Intel, essentially said, look, the way it's going is we're going to double our computing power every 18 months. What they mean by that, people misunderstand what they mean by it. What they mean by that is every 18 months, that the transistors on a computer, CPU or RAM, but mainly CPUs they're talking about, will get twice as small. It'll half every time, so it's exponential. Okay, and that's what he means. The transistors are going to get smaller and smaller and smaller, and you can see that they're always getting smaller. I mean, 5 years ago, the best CPU you could get was 34 nanometers. Yeah? Now it's 14. So they went from 34 nanometers, I think, to 28. To 20, now they're at 14. Intel announced this week that in the second half of 2019, they're going to be at 10 nanometers. Right now, they're at 14 nanometers. By 2019, they're going to be at 10 nanometers. That means a third smaller, almost a third smaller. That's pretty good. Once they start getting below 10 nanometers, the technology actually has to change for them to get smaller and smaller. And when they're talking about Moore's Law, that's what they're talking about. And it has actually happened. I mean, every 18 months, those transistors or registers that they're able to burn through lithography in the CPUs half in size. That's what they mean by Moore's Law. And Moore's Law is still valid today. I mean, beyond Moore's Law, I think it's still going to be valid for another 50 years because then you get into quantum computing. And then Moore's Law is still, our computing power doubles doubles every 18 months. And with quantum computing, when we get below 10 nanometers in our register size, if we have to move to quantum computing, which they've been working on for years, to continue with that progress, technical progress, I think Moore's Law will still be valid, especially when we go to quantum computing. I mean, if you look at Moore's Law, it hasn't been wrong since it was introduced. And it's not as tight as you think, 18 months or 2 years. And he means ballpark double, right? But it's continually been happening since his prediction. I'm Johnny O. Don't forget to like and subscribe. I'll see you next time.